This is Chapter 4, Section 1, Studying Atoms. If you'll notice, our reading focus or our key concepts that we'll be picking up on are what was Dalton's theory of the structure of matter, and what contributions did Thomson and Rutherford make to the development of atomic theory. Says studying the structure of atoms is a little like studying wind because you cannot see air. You must use indirect evidence to tell the direction of the wind. You might notice which way fallen leaves move as they are pushed by the wind and infer that the leaves and wind are moving in the same direction. Atoms pose a similar problem because they are extremely small. Even with a microscope, scientists cannot see the structure of an atom. In this chapter, you will find out how John Dalton, J. Thomson, Ernest Rutherford, Niels Bohr, and other scientists used evidence from experiments to develop models of atoms. Ancient Greek models of atoms. If you cut a piece of aluminum foil in half, you have two smaller pieces of the same shiny, flexible substance. You could cut the pieces again and again. Can you keep dividing the aluminum into smaller pieces? Greek philosophers debated a similar question about 2,500 years ago. The philosopher Democritus believed that all matter consisted of extremely small particles that could not be divided. He called these particles atoms from the Greek word atomos, which means uncut or indivisible. He thought there were different types of atoms with specific sets of properties. The atoms in liquids, for example, were round and smooth, but the atoms in solids were rough and prickly. Aristotle did not think there was a limit to the number of times matter could be divided. Figure 1 shows the model Aristotle used to describe matter. For many centuries, most people accepted Aristotle's views in the structure of matter, but by the 1800s, scientists had enough data from experiments to support an atomic model of matter. So if you look over here at Figure 1, here's this picture. Okay, it says Figure 1, Aristotle thought that all substances were built up from only four elements: earth, air, fire, and water. These elements were a combination of four qualities: hot, cold, dry, and wet. Fire was a combination of hot and dry. Water was a combination of cold and wet. So, if you really think about this, that would make sense to a lot of people. Because they could see fire, they could see water, they could see the earth, and knew that there was air around them. So, really, that made more sense than Democritus's awesome explanation of thinking that there were particles that were very small. And so, and Aristotle rocked the house on a lot of things anyway. He was known for many things and philosophized very good. So, anyway, on to the next section. So now we're going to start looking at Dalton's atomic theory. Okay, so go to the next page. Dalton's atomic theory. John Dalton was born in England in 1766. He was a teacher who spent his spare time doing scientific experiments. Because of his interest in predicting the weather, Dalton studied the behavior of gases in air. Based on the way gases exert pressure, Dalton correctly concluded that a gas consists of individual particles. Evidence for atoms. Dalton gathered evidence for the existence of atoms by measuring the masses of elements that combine when compounds form. He noticed that all compounds have something in common. No matter how large or small the sample, the ratio of the masses of the elements in the compound is always the same. In other words, compounds have a fixed composition. For example, when magnesium burns, as shown in figure 2, up here in this corner, It combines with oxygen. The product of this change is a white solid called magnesium oxide. A 100-gram sample of magnesium combines with 65.8 grams of oxygen. A 10-gram sample of magnesium combines with 6.58 grams of oxygen. The ratio of the mass of magnesium to the mass of oxygen is constant in magnesium oxide. So essentially what they're saying is he was actually able to find the mass, and he could tell that every time there was magnesium oxide it combined in the same way, which is awesome. Dalton's theory. Dalton developed a theory to explain why the elements in a compound always join in the same way. Dalton proposed the theory that all matter is made up of individual particles called atoms, which cannot be divided. The main points of Dalton's theory are as follows. Elements are all composed of atoms. All atoms of the same element have the same mass, and atoms of different elements have different masses. Compounds contain atoms of more than one element, and in a particular compound, atoms of different elements always combine in the same way. In the model of atoms based on Dalton's theory, the elements are pictured as solid spheres like those in figure 3. Okay, this picture over here. Each type of atom is represented by a tiny solid sphere with a different mass. Recall that a theory must explain the data from many experiments. Because Dalton's atomic theory met that goal, the theory became widely accepted. Over time, scientists found that not all of Dalton's ideas about atoms were completely correct, but this did not cause later scientists to discard the atomic theory. Instead, they revised the theory to take into account new discoveries. Okay, and there are the wooden spheres. This would be Dalton's model. Thomson's model of the atom, right here. When some materials are rubbed, they gain the ability to attract or repel other materials. Glass and the amber in figure 4 have this property. Based on their behavior, such materials are said to have either a positive or a negative electric charge. Objects with like charges repel or push apart. Objects with opposite charges attract or pull together. Some charged particles can flow from one location to another. A flow of charged particles is called an electric current. When you turn on an appliance such as a hair dryer, a current flows from the wall socket through the appliance. Joseph John Thomson, 1856 to 1940, better known as J.J. Thomson, used an electric current to learn more about atoms. And there's the picture they were referring to. Thomson's experiments. Thomson used a device like the one shown in figure 5a. At the center of the device is a sealed glass tube from which most of the air has been removed. There is a metal disc at each end of the tube. Wires connect the metal disc to a source of electric current. When the current is turned on, one disc becomes negatively charged and the other disc becomes positively charged. A glowing beam appears in the space between the discs. Thomson hypothesized that the beam was a stream of charged particles that interacted with the air in the tube and caused the air to glow. In one experiment Thomson did to test his hypothesis, he placed a pair of charged metal plates on either side of the glass tube, as shown in figure 5b. The plates caused the beam to deflect or bend from its straight path. Thomson observed that the beam was repelled by the negatively charged plate and attracted by the positively charged plate. Okay, so here's a picture of that experiment on A and B. That's his experiment that he used. Evidence for subatomic particles. And so here, let me show you here. Figure B, Thomson used a sealed tube of gas in his experiments. A, when the current was on, the disc became charged and a glowing beam appeared in the tube. Then if you look at B, the beam bent toward a positively charged plate placed outside the tube. Okay? Evidence for subatomic particles. Thomson concluded that the particles in the beam had a negative charge because they were attracted to the positive plate. He hypothesized that the particles came from inside atoms. He had two pieces of evidence to support his hypothesis. No matter what metal Thomson used for the disk, the particles produced were identical. The particles had about 1 in 2,000 the mass of a hydrogen atom, the lightest atom. Thomson's discovery changed how scientists thought about atoms. Before his experiments, the accepted model of the atom was a solid ball of matter that could not be divided into smaller parts. Thomson's experiments provided the first evidence that atoms are made of even smaller particles. Thomson revised Dalton's model to account for these subatomic particles. Thomson's model. An atom is neutral, meaning it has neither a negative nor a positive charge. How can an atom contain negative particles and still be neutral? There must be some positive charge in the atom. In Thomson's model of the atom, the negative charges were evenly scattered throughout an atom filled with a positively charged mass of matter. The model is called the plum pudding model, after a traditional English dessert. You might prefer to think of Thomson's model as the chocolate chip ice cream model. Think of the chocolate chips in figure 6 as the negative particles of the vanilla ice cream. Think Think of the chocolate chips in figure 6 as the negative particles and the vanilla ice cream as the positively charged mass of matter. When the chocolate chips are spread evenly throughout the ice cream, their negative charges balance out the positive charge of the vanilla ice cream. Rutherford's atomic theory. When you try something new, you may have expectations about the outcome. Does the outcome always meet your expectations, or are you sometimes surprised? Scientists can also be surprised by the results of their experiments, but unexpected results can lead to important discoveries. This is what happened to Ernest Rutherford. Rutherford's hypothesis. In 1899, Ernest Rutherford discovered that uranium emits fast-moving particles that have a positive charge. He named them alpha particles. In 1909, Rutherford asked one of his students, Ernest Marsden, to find out what happens to alpha particles when they pass through a thin sheet of gold. Recall that in Thomson's model of the atom, the mass and positive charge are evenly spread throughout an atom. Based on this model, Rutherford hypothesized that the mass and charge at any location in the gold would be too small to change the path of an alpha particle. He predicted that most particles would travel in a straight path from their source to a screen that lit up when struck. Those few that did not pass straight through would be deflected only slightly. The gold foil experiment. Marsden used the equipment shown in figure 7. He aimed a narrow beam of alpha particles at the gold. The screen around the gold was made of a material that produced a flash of light when struck by a fast-moving alpha particle. By observing the flash, Marsden could figure out the path of an alpha particle after it passed through the gold. Some of the locations of the flashes on the screen did not support Rutherford's prediction. More particles were deflected than he expected. About 1 out of every 20,000 was deflected by more than 90 degrees. Some of the alpha particles behaved as though they had struck an object and bounced straight back. Okay, so that definitely was not something that he expected at all. Discovery of the nucleus. The alpha particles whose path were deflected must have come close to another charged object. The closer they came, the greater the deflection was. But many alpha particles passed through the gold without being deflected. From these results, Rutherford concluded that the positive charge of an atom is not evenly spread throughout the atom. It is concentrated in the very small central area that Rutherford called the nucleus. The nucleus is a dense, positively charged mass located in the center of the atom. The plural of nucleus is nuclei. Because Thomson's model no longer explained all the evidence, Rutherford proposed a new model. According to Rutherford's model, all of an atom's positive charge is concentrated in its nucleus. The alpha particles whose path were deflected by more than 90 degrees came very close to a nucleus. The alpha particles whose paths were not bent moved through the space surrounding the nuclei without coming very close to any nucleus. Figure 8 shows the inside of the Astrodome, a domed stadium in Houston, Texas. The roof of the stadium rises to a height of 202 feet above the center of the field. If an atom had the same volume as the stadium, its nucleus would have the volume of a marble. The total volume of an atom is about 1,000,000,000,000 times the volume of its nucleus. Okay, so that is the end of